we do the topic, process synchronization, you must be knowing uh, what is a process, okay? And how many types of processes are there in an operating system? Did we talk this in the class before? How many types of processes are there in an operating system?
Mm,
How many types of processes are there? Two types, that is independent process and cooperating process, if you remember. Okay, so what is process synchronization? First of all, we have to see. So it is a kind of a method which is used to coordinate the process that uses shared data. Okay, so process synchronization is a method which is used to coordinate among process for those processes which have a common data among them. Okay, so when we talk about types of processes, there are two processes: independent process and cooperating process. So in case of independent process, there is no common sharing or no common code or no common resources that is shared between any two process or a group of processes. Okay, they're completely different. They have independent work, and there is nothing shared between the processes. So that's why they're saying that example is the process that does not have any shared variable database files or any kind of resources. All right. Now, in case of cooperating process, it is a kind of process where the execution of one process will affect the other. So there is a dependency among them. Okay, so whenever a process, one process is executed, so that execution will have an impact on some certain other process. Now, why is it so? The main reason for this is because they share various elements like variables. It can be memory. It can be a part of a code of a program. That means a program, a part of the code of a particular program may be common for two different processes. So that time that may occur some kind of inconsistency. So that basically we have to overcome. Okay, also sometimes if we are sharing certain resources, like for example CPU, printer, or hardware elements, then that time also there has to be a synchronization among the processes. Otherwise, whatever the output we are supposed to get, that would not be achieved. Okay, so for example, here they're given a code. So this code I have simplified and written here. So let us say, suppose we are having two processes, P1 and P2. Okay, so it is kind of a code snippet. Now here at the top, if you can see here, there is a global variable. This is a global variable. So we have a global variable shared, called shared, and its value is assigned to be equal to 5. Okay, now at this situation, let's see for process P1, what is it happening in process P1? So here x is a local variable under P1, and it is getting the value of shared. So what is the value of shared? What is the value of shared? We know that shared is a global variable and it is having value 5. So under this, under process P1, we are having certain code. So first instruction, what do we have? We have integer x. So x is a local variable, and it is assigned the value of shared. So shared we already know from here. What is the value of shared? The value of shared is 5. So 5 will be assigned in x. So x here is equal to 5. So I can comment maybe. So here I can say x is equal to 5. Okay. Now in the second line of instruction, what do I have? I say x plus plus. That means x will be incremented, right? Isn't it? So the new value after incrementing, what will we have? X is equal to 6. Okay, so let me comment here. Okay, now third instruction, construction, what do I have? Sleep. That means I'm calling a function which will basically suspend this process P1 for maybe for 1 unit of time. It may be 1 minute or 1 second. And then this part of the process will be sleeping. That means process P1 will go for sleep. It will be preempted. There will be a suspension. So the moment this is executed, the moment the third line is executed, so what will happen is basically there will be a kind of suspension. So that means process P1 will be halted for some time. Suspension of P1 for, let's say, 1 second. Okay, so after this, what will happen? Then the operating system will check that do we have any alternate process which is waiting? Yes, we do have. So what is the alternate process? P2. So the control will come here. That means this P1 is suspended and we are giving the control to P2. Okay, so this switching from one process to another is known as your context switching. Now again here, the first line of instruction, what does it says? Integer y is equal to shared. That means y will be assigned the value of shared, but shared I already know what is the global variable of shared, 5. So here I'll have y is assigned the value of shared. So y's value will be how much? 5. Okay. Then y is decremented. Y is decremented. So initially y was having 5. So now what will be the value of 5? Y value will be 4. Okay. Then again in the third line of instruction, what will happen? We will encounter sleep function which will suspend P2. So this again same thing. So it will suspend P2 for how much? For maybe 1 second or 1 minute, depending upon the unit. So this will again go for suspension of P2 for, let's say, 1 second. Okay, so this is suspended. That means P2 will not be executed. So again, there will be a context switch. That means it will come here to the fourth line because the other three lines of P1 are already executed. So now, what is the fourth line saying? It is saying that shared will be assigned the value of 6. So that means what will be the value of shared now after the uh, uh, after this execution of statement. So x we already found. What was the value of x here? 6. So 6 will be stored inside this one. So we got from this first instruction set that the value of shared now has become how much? From 5. What did we get? 6. So this line is executed. Now, once this is over, then P2 is still yet to be done, right? It has not finished. So what will it do? Again, there will be a context switch here. This is done now. P1 will not come anymore. So shared is assigned to Y. So that means again shared in P2, shared is updated with something else. So is it same or different? Let us see. So shared is equal to, what is it? Shared is equal to y. But what is my y? So y is 4. Okay. So ultimately from here we are getting the value of shared to be equal to 4. Okay. Now, what is the problem here? When I compare this results, okay, so what will happen is, first of all, this value 4, this value 4, is it correct? This value 4, is it correct? No. Why? Because initially we were having 5. 5, if we see here, 5 plus 1 is how much? 6. There was a context switch. It went there. Okay. And there was a decrement of 1 unit. So 6 minus 1, it should have been 5. Okay, that means this should have been 5, but we are getting 4, isn't it? So now what will be there? There will be an anomaly because correct result was not found. So why this happened? Because there was no synchronization between the two processes. Okay, one is sleeping, the other is coming, the other is sleeping, the other is going, but there is no coordination among the two. What is happening? The two they don't know, or there is no synchronization. Okay, so such kind of situation where if you see here, both 4, 6 and 4, the value of share, that is 6 and 4, both are competing, or you can say are racing. Okay, like who will be getting the ultimate, you can say, will be considered as the ultimate output. So this condition is known as your race condition. Okay, so this basically happens only with cooperating processes. Why? Because there are certain things which are common. So here what was common? That shared variable was common. So that's why whenever we are dealing with common things, then that time whenever updation takes place, so there may be an anomaly. Like in this case, it happens. Okay, so if we execute such kind of program, so we will see that in certain operating system we are getting value 4, in certain cases we are getting 6. Okay, so this is basically why, because there is no synchronization between the two processes. Okay, so to overcome that, basically we have process synchronization. All right. Now, whenever like a code is being executed, okay, so let's see. Mm, okay, this is race condition. Okay, now whenever we are going for process synchronization, then certain things we have to know. Okay, so what are those things? First of all, so what is it trying to say? Race condition is the condition where several processes tries to access the common resources and modify the shared data together, and the outcome of the process depends on the particular order of execution. Very here also, whatever value we got here 6, and whatever value we got here 4, it was dependent upon the order. First it incremented, it went to a sleep mode, then it came here, it was decremented. Okay, so that order depends. Suppose if sleep would have occurred at the second line only, and this one would have been in the third line, then this value would have been different that time. So every code that we write in a program, like in especially in case of cooperating process, the order of the code is very very important. Okay, otherwise it will lead to data inconsistency, and this kind of situation basically we call it as a race condition. So this condition, as we said, we can avoid it by using process synchronization. So in process synchronization, what do? We allow only one process. Okay, so in process synchronization, what do? We allow only one process to enter and change that shared data in critical section. Okay, so again, I'm saying race condition, we already have seen that it leads to data inconsistency for shared variable or shared part of the coding. Okay, so to overcome that, we have what? Process synchronization. So how do we synchronize or arrange the processes? Okay, while executing, what we do is, whenever the processes are executing, only one process is allowed to enter and update the shared part of the data. In a program, there can be some codes which are not dealing with shared data. Okay, like for example, this sleep, or maybe the increment part, or maybe let's say in a big program, only certain parts of the program may have the shared data by 2 or 3 processes. But for what about the other parts which does not have the shared data, the other part of the code which does not, that we can leave it. That's not a problem. Okay, but the only problem will arise only for the shared data. So if suppose we have certain like this, then we will allow only one process out of all the processes. We will allow only one process to enter the data and change or update the data in the critical section. Okay, so like for example here, uh, we are having there how many sections? 1, 2, 3, 4, 5, and critical section is like the core. Okay, so in critical section, what happens is, uh, critical section, it's a part of the program where shared resources are accessed by various processes. So it is a place where shared variable resources are placed. Okay, so in the critical section, I can also say what they have written here. It is a part in which only one process is allowed to enter. That means in this critical section, only one process can enter. Like for example here, how many processes were there? 2. So out of the 2 process, if suppose someone has to enter into the critical section, then only one can enter. in one particular instant of time. Okay, so it is a part in which only one process is allowed to enter and modify the shared variable. So here also we have seen there was shared variable. This was the shared variable called shared only. Okay, because it was shared among the two processes. So only the shared variable, only one process is allowed to enter, and that process will be able to change or modify or update the shared variable. This part of the process ensures that only no other process can access the resource of the shared data. So until and unless the process is inside the critical section, so other processes will not be allowed to access that shared data at that period of time. It will be locked, something like that. Are you getting the point? Okay. But then how do we decide, like there may be two processes, there may be three processes, so how do we decide? So what we do is, we may have in a program, or let's say for example in a process, let's say for example in a code, like for example here. Okay, there will be a section, like for there will be a section called entry. Let's say I'm just writing here. Let's say there is a function called entry. Okay, so what is the role of this entry function? Basically, it will tell the operating system, like it will basically hint, or it will prompt the operating system that once we reach that part of the code, then the entry of a particular process in the critical section must be done out of many other processes. Like for example here, let's say the entry is here. Okay, and suppose I got let's say the entry segment. Okay, entry is also a piece of code. So I'm just showing kind of with this function. So let's say out of these processes, P1 and P2, while this is being executed, okay, so first suppose this one is executed, or let's say, let me, so entry I'm saying again, it is a part of the process. Every process will have a code which will basically signal the operating system that the process has to be fed into the critical section. So once suppose P1 is scanned, so what is it seen? Oh, it has seen that there is an entry function, or maybe an entry code is written. So the moment this is seen as a part of the instruction, it will be prompting the operating system that the process has to be, I mean to say, the shared part of the shared part of the process must be taken, okay, to the critical section. So that's why it is saying entry section, it is the part of the process only, okay, which decide. That means it is a part of the process means what? It is a code will be there for the entry section, which will decide the entry of that process in the critical section out of many other processes. Okay, so once you have prompted in the code that I have reached the entry section, so automatically that process will be loaded in the critical section and will be executed. Okay, so how long will it execute? That is the question. Okay, once it is in the critical section, how long will it load? That is also a question. So it will be continuing until and unless it does not reaches the exit section. That means once the shared part of the variable is accessed, manipulated, okay, and updated, then after that there will be a quote in the program only, which will basically again prompt the operating system that it needs to come out. That means that process has to be released from the critical section. Okay, so once that exit section is encountered by the OS, so that process is released from the from the critical section, making way for other processes. So once it is done, its work from critical section, it will come here into the exit section. That means it has finished the shared part of the program. Now it will there will be a quote in the program only which will say that okay, I have reached the end, so I should be exiting. So once that process exits from there, so what will happen? There will be a remainder section. So what will the remainder section do? It will keep track of the other processes which has not been completed so far. So what will that do? First of all, what will that have is, first of all, we talk about types of process. We said there are two types, independent process and cooperative process. In independent process, we don't have to worry because one process is not affected by the other process. Okay, its execution is independent. There is no sharing of anything. In cooperative process, there is sharing of resources, there is sharing of data, sharing of various data, sharing of hardware devices as well. So in this case, what happens is there may be kind of inconsistency in data or some like we have seen. There may be not two different values that we got here. We got 6, we got here, but we should have got 7 because there is one increment of addition. But we don't know yet. We got 6 and 4. Now, which one is correct? We cannot decide, right? Because both will be racing, both will be competing for proving themselves that they are right. Okay, so some of the operating systems may give us value 6, some of the operating system may give us value 4. So in this situation, when both the final output is racing to prove themselves that they are correct, so we say that this is a race condition. Okay, so it's which is not good because there is an inconsistency in data. Correct output was not produced. Then what do we do? Then in that case, we have to look for certain solutions. Okay, and this happens basically with cooperating processes only. So to solve this condition, we kind of raise a concept called critical section. Okay, there is a concept called critical section. So critical section is what? It is a part of the code only. It is a part of the code in which one process is allowed to enter and modify the data or the variable which has been shared between two or three processes. Once the updation or manipulation of that shared data is done, then it can exit from that critical section and other processes can request. Okay, now how this takes place, the request and the exit. Okay, so what happens in the C code only, or in whatever language code you have written, that code will be divided into various sections. One section is where we are writing the shared variable, that means the part of the C code where uh, 2 3 processes are accessing that variable. Then certain parts of the code will be there which has got non-shared portion, that means local variables only are there where it is non-shared, it is not shared between the other processes, so that doesn't matter, it will keep on executing, you can say parallelly, because there is no dependency, so there is no problem. So once suppose we have reached a part of the shared variable, so before that only there should be a code which will tell the operating system that this process is basically ready to be put into the critical section problem. Okay, so there will be a code in the entry section. Okay, so there will be a code in the program only, which is called as the entry section. The moment that code is scanned, okay, so it will be notified to the OS that now, this process has to be put into the critical section. If a situation comes, like for example, two of them are like saying process P1 also, process P2 also. Is it possible that both of them can be saying at the same time to this one should take this one should be taken? Is it possible that both of them will be requesting that I'll this like entry section it has both of them has encountered? Can that be possible? Can that be possible? That both are requesting that it has to be put in the critical section? Can it be possible in case of any processor is running? It's not possible. Okay. Why? So in one time only, one process only can be allocated to the critical section. Okay, so that's why according who is making the entry section request, based on that only we are keeping the process into the critical section. So it will be executing, manipulating the data. Once the data has been manipulated, updated, so what will it be doing? The next line of instruction is the exit section of the program. So that exit section will basically tell the OS that the process execution is done, that can be removed from the critical section. Okay, So in remainder section, what will be there? The program is divided into three parts: entry section, critical section, and exit section. Entry section also we have to write certain coding. Critical section also we have to write certain coding. Exit section also we have to write certain coding. Leaving all this, whatever other parts of the program are remaining, that is the remainder section of a program. That means one program has been subdivided into four different regions. Are you getting? Okay. Then certain factors that critical section must be satisfying. Okay, so first is mutual exclusion. So mutual exclusion, you will not stress much, I think by now you know what is mutual exclusion. It states that no other process is allowed to execute in the critical section if suppose some other process is already present there and it's being executed. Okay, so that's called mutual exclusion. That means one process, if it's already there in the critical section, then other processes has to wait until and unless that process is not yet done and it's not yet it has not yet come out from the critical section. So that condition basically is set as your mutual exclusion. Is the progress. Okay, so what does it says? When no process is in the critical section, then when no process, that means no processes are there, then any process from outside that request for execution can enter in the critical section without any delay. So suppose if there is no process at all in the critical section region, then it's fine. Then whoever process will make the first request, that process will be given the priority and can enter into the critical section. Only those process can enter that have requested, that is clear, and have finite time to enter the process. Okay, so it's not that the process should take a very long execution period of time. So that should be avoided. Okay, so anyone who makes the first request and whose best time is pretty much reasonable, so accordingly that process can be allowed to enter into the critical section. Okay, so these are the conditions that critical section problems must satisfy. Then another one is bounded waiting. So what happens is bounded waiting. An upper bound must exist on the number of times a process enters so that other processes are allowed to enter the critical sections after a process has made a request to enter its critical section and before that request is granted. Okay, so let us say for example, we have two processes P1 and P2. Okay, now let's say P1 has entered into the critical section, it has executed and it has exited from the critical section region. Now, who should have got the chance to enter the critical section? P2. But what has happened again? P1 has entered, it has executed, and the critical section region, and then it has exited. Third time also only P1 is only getting the opportunity for entering, execution and exiting. P2 has to wait. For how long it has to wait? For an infinite number of time. So this kind of, you can say, anomalies should be avoided. And while designing the critical section coding, the programmer has to make sure that such kind of, you can say, improper distribution of execution of processes must be avoided. Okay, so that's why this is called bounded wait. That means a process can wait, but for a finite number of time. It may so happen that P1 is given, it's okay, first, second, three times it is given to execute, then fourth time P2 is given, then again six, then again five, six, seven, three times P1 executes, and then again for one time P2 executes. So for finite time it's okay. Three times P1, one time P2. Three times P1, one. That way it's okay. Or two times P1, one time. That way it's okay. But if it is wait for 20 units of time, or if it has to wait for more larger than that, infinite number of times, or 100 number of times, then only P2 will get the scope to execute, to enter. So this kind of problems should be handled by the programmer while writing the code, so that you can say process synchronization can be obtained. Okay, so any problem you can write in the comment section. Algorithms, I'll be discussing like separately all of them because there are too plenty. So that's why I'll be discussing like in different class altogether, because I have to make like examples also in Word, MS Word. Okay. So can I proceed towards the next topic? Okay. So next topic that we have is is your semaphores. Okay. So let us see the brief history first. So semaphore was proposed by Dijkstra in 1765. Important technique like parallel processes if they are running to at the same period of time by using a simple integer value which is known as semaphore. Okay. So semaphore is just a value basically used to indicate that whether a particular region of the code is ready for execution in the critical section, or whether it's not yet ready. Okay. So it is basically used in multi-processing environment. Now semaphores, as we said, that it is a integer variable element, isn't it? It is non-negative. That means its value can never be negative. Okay. It is used for mutual exclusive process. That means if one process is running, the other one should not be executing. Okay. Used by only cooperative processes. Okay. As per the theory, there are two types of semaphore. One is the binary semaphore, okay, and the other one is the counting semaphore. So binary semaphore, from the name itself, it will have only its value is always initialized at the beginning to be one. Okay, and this is basically used to implement the solution of critical section problem if we have multiple processes.
Sir,
Okay, counting semaphore, yes. Tell me.
Sir Nihal has asked a question in doubts.
Okay, let me check. Okay, bounded again, no? All right. Okay, so when we talk about bounded weighting, okay, so suppose for example, as I said, let's say we have two processes, P1 and P2. Okay, now let's say for example, if P1 has entered into the critical section, it has executed, he has done its work, it has come out. Okay, so P1 has done. So who should be given the priority next? Should be given P2. Okay, but what has happened next time again? P1 has entered into the critical section, it has executed its code, and then it has come out. So third time also, fourth time also, it has been doing, and this kind of repetition has taken place for, let's say, 20 number of times or 30 number of times, and it kept P2 waiting. But this should not have happened, because whenever a particular process has to execute a critical section, maybe we can give him a second chance, or maybe at most three chances. Okay, but the other processes also should be given fair amount of scope to enter into the critical section and perform its work. But what has happened here is P1 has always like taken the opportunity, and it is making use of the critical section. Okay, so keeping P2 waiting. So this kind of like problem, basically we handle it using bounded waiting. That means, okay, P2 can wait, but there will be a specific amount of time. Let's say, for example, P2 can wait, let's say, if P1 has executed for two times or three times, but there will be a limit. That's why it's called bound, limit based. Okay. So let's say we can give permission that P1 can execute at most for three times. So after three, you can say three times of usage of critical section by P1, then P2 will be given the scope. Again, next time, three times P1 will be using P2 that way. But it will not be that P2 has to keep it waiting till when P1 will release the system. So it's not like that. Okay. So this kind of, you can say, tackling of range, that how much one process can execute. Okay. The critical section of a region, this is called your bounded waiting. So does it clear the? Okay, so I'll just give this link. So this will basically give you process synchronization and critical section. Okay. Then next comes is the semaphore. So what is a semaphore? We have already seen. It was proposed by Dijkstra in 1965. It's a method to manage processes which are running concurrently by using a small integer value. The values are always non-negative and they can be shared between threads as well. Okay, it is basically used to solve critical section problem. Okay, so as we said that there are two kinds types of semaphore, binary and counting. So in binary, the value of these semaphores is zeros and ones only. Okay, and its initial value is said to be one. Okay, it is said to implement solution of critical section problem with multiple processes. So we will see how does it work. And another kind is counting semaphore, so its value can range over a unlimited domain. Okay, it's not a 0 and 1, it can be 999, it can be 3, it can be 4, depending upon how many processes we have. So depending upon the number of processes that we have, so the value of the semaphore is kept. Okay, so it is used to control access to a resource that has multiple instances. So what does it mean? We may have one resource that, let's say, four processes are trying to access. Here instance means process. So that's what the meaning is. It is used to control access to a resource. So one resource can be available to one process only at one point of time. So if there are four processes which are trying to access the same resource, so here the semaphore value will be 4. Okay. So let's say, for example, we are having here this piece of this code. So if you look here, there are two sections. One is P. So P is basically the wait function, I can say, the wait part of the program. V is basically the signal. Okay, so there are two things that we need to know. One is the P operation, also called as wait, sleep, or down, and V operation is called as the signal or wake up or up operation. Okay, both the operations are atomic, and a semaphore value, as we said, that it's initialized to 1. Okay, so when I say that the operations are atomic, what does it mean? Atomic means what? That means if suppose, let's say, if suppose a variable, okay, suppose if it is in a write mode or read mode, okay, suppose it's being let's say, for example, there may be some kind of operations that is being performed, okay, in a particular variable, whatever the operations it may be. It can be write, it can be read, it can be append, whatever it may be. So that operation can be only one. It cannot happen that multiple operations are taking place at the same period of time. Okay, so that's why the thing they are saying is that the operations are atomic. That means at one instant of time, only one operation is possible. Operation can be any. It can be read, it can be write, it can be update, like what they have written here. Okay, but no other operation will be, you can say, given the accessibility to change the variable. At one point of time, only one type of operation is performed. Okay, so that's what this is one of the characteristic of semaphore. A critical section is surrounded by both operations. So for example, we may have very big code, But that part of the code of the C program which has the shared variable, so that will be entered into the critical section. So a critical inside the critical section we will have both the operations. That means P also as well as V. P means the wait operation as well as the signal operation. Okay, so let us say for example, we are having here uh, this block of block diagram. So critical section is surrounded by both operations to implement process synchronization, that we already know. Okay, so in this image what we are having, critical section of process P is in between P and V. Okay, so this P oblique like S is basically the operation, the wait operation. This P is the process P, this bold one. Okay, this P and this PS is not same. This PS is the operation. Which operation? The wait operation. And this P is basically this bold letter one. P is basically the process P. So this is the operation of the semaphore S. Okay, that is the difference. Then V is what? It is the P of the semaphore S. Okay, that is the difference. Then V is what? It is the signal. So let us see how it is being implemented. Okay, so let us see how it implements mutual exclusion. So let there be two processes, P1 and P2, and a semaphore S is initialized as 1. So one thing we have to remember is that it doesn't mean that for if there are two processes, then semaphore also will be 2. If suppose if the two processes are linked together, if they are cooperating, that means they are sharing some certain variable, they are having certain common, then to maintain that synchronization only one semaphore is sufficient. Okay, so now if suppose P1 enters in its critical section, then the value of semaphore S will become 0. So what will this indicate? It will indicate that if suppose P2 wants to enter the critical section, it cannot enter. What is the reason? Because it will see what is the value of semaphore. Oh, semaphore's value is 0. That means if the semaphore value is 0, what will it indicate? It will mean that critical section is occupied by some process. That will be the signal which will go to P2. Okay, so it has to wait until and unless the value of the semaphore becomes 1 or greater than 0, because we know that the default value of semaphore is what? 1. So when the default value of semaphore is 1 means what? The critical section is free, there is nothing. Okay, once the semaphore value becomes equal to 0, then what message is sending to other processes? It will be sending the signal that no, we have to wait, because semaphore value meaning semaphore value being 0, it means that some process is already there in the critical section, so we will not be able to enter, because in critical section only one process can enter at one time. Okay, so that's why P2 has to wait until and unless the value of that semaphore changes to something else. That means greater than 0, because semaphore value can never be negative, so it has to be greater than 0. So this can only happen when the process P1, which is there inside the critical section, will leave it. So once it leaves, or before it leaves, it has to notify. So how will it notify? It will call its this operation V. It will call the operation V. So V is what? It is the signal. That means it is the signal which will tell the other processes that it has released the critical section. Okay, so this way the mutual exclusion is achieved. So whenever suppose here in this block diagram also they have said we have different kind of situations. First situation is, let's say P1 P2 both have not entered, so by default the value of semaphore will be what? 1 only, because no one is there. Now if P1 has entered into the critical section, so automatically semaphore value will be 0. It will keep track of this one. So if P2 wants to enter, it will check, let me check semaphore value, what is its value. So it will see, okay, semaphore is 0, that means someone is there, so I cannot enter. Then next time again, let's say for example P2 again if wants to check that whether it is free or not, so it will again look back, it will do a lookup whether I can enter or not. I can still not enter, so this semaphore value will be still 0, so P2 will be restricted. Then the fourth time, if once P1 has finished execution, it has come out, it has given the signal v also, v signal also is generated, that means it has released the critical section area. And so what will happen, this semaphore value will be updated. So again, after some time, when p2 will do a lookup, it will see, okay, s is 1 is 0, that means now I can go to the critical section. Okay, so that is how binary semaphore works. Now one more thing you have to remember, it's not that P1 only can enter first. P2 also can enter. So if P2 is entering, is entered, then semaphore value will be changed. It will be 0. So if P1 wants to enter that time, it also has to cross reference the semaphore value. So if the value is 0, then even P1 has to wait until and unless P2 has finished. And once it has finished, so that semaphore value is updated. Then when these signals will come into play, this which are the two signals, oh sorry, operations, p operation and v operation. P operation will take place once before the process is just about to enter. Okay, so that means this operation will basically make others processes aware that you have to wait, or you have to sleep, or you have to rest, or whatever, you have to be down. Okay, you have to think. And v operation, basically once the mm, work is done inside the critical section, and after coming out, then it can send the signals. Okay, so it's a kind of an operation which basically, it's basically for notification purpose only to the other cooperating process that they can start. Okay, then another semaphore was what kind of semaphore was there? I think it
It
was
was
the
the
counting
counting
semaphore. Okay, so this kind of semaphore, the binary semaphore,
semaphore
is
is
okay
okay
for,
for,
let's
let's
say,
say,
when
when
you
you
have
have
processes, lesser number of processes. Okay, that time you can change the values. Okay, and it's much more efficient. But let's say if we are having a situation like there is only one single resource, but the number of processes is 4. Okay, so that time that binary may not be very efficient, so we have to go for counting semaphore. So here, what is the only difference? The difference is that we initialize the value of the semaphore as 1, and the rest of the working is same only as binary semaphore. Okay, so as value will be taken depending upon how many number of processes are there. Okay, so whenever process wants that resource, it calls p or wait function, and when it is done, same thing, it will release v or signal function. So if the value of s becomes 0, then a process has to wait until s becomes positive. For example, suppose if there are 4 processes, P1, P2, P3, P4, and they all call wait operation on S. If another process, P5, wants the resource, that it should wait until one of the 4 reprocessors call signal function and value of the semaphore becomes positive. So same thing only. If suppose we are having 4 processes here, okay, let's say for example, so the value of this process will be how much? 4. Now, suppose if one more process comes and it wants to access that resource. So, what will it do? It cannot access until and unless the value of the semaphore becomes less than 4. Okay, there it was less, I think it was between 0 and 1. 1 was for empty and 0 was for um, this thing, what is it called? For the process which is there in the critical section. So in this case, it will not check for 0. It will just check whether the process is, let's say, lesser than the total number of processes. Let's say 4 processes are there, and all of them have called for the S operation. So if another process wants the resource, then it will have to wait until one of the 4 processes will call the signal function, and the value of the semaphore will become positive. Okay, these things are not required. Okay, one thing. mm, this is important. Advantage, limitation. Sorry, what is the disadvantage of a semaphore? one of the biggest disadvantage of semaphore is priority inversion. So what do we mean by priority inversion? Suppose when we have a low priority process, okay, which has own a semaphore, and let's say a high priority task has to be executed first. So the semaphore then cannot decide like which one to give, because once you are implementing a semaphore, then you low priority semaphore has a low priority process has requested, okay, and once suppose if you have given that low priority process to enter into the critical section, and if a high priority process requests that no, I want to be executed, it cannot make a decision, then we cannot do anything. Why? Because it is all dependent upon the semaphore value. The moment the value of semaphore is you can say 1, that time only we will be able to I mean to say I'll take in another process. So here the priority basis of processing does not take place. So this is one of the biggest disadvantage, okay. Then there is a chance of resources utilization also, because every time the OS has to keep a lot of track of the calls, of the notifications, like the wait and the other signal as well. So these kind of, for a big kind of program or a piece of code, or if we are, if suppose multiple processes are there in a system, okay, then that time maintaining these kind of notifications is little bit you can say time consuming, resource consuming for the OS. So these can be certain limitations which may be there. Another one may be, it may so happen that let's say for example 2 3 processes there, okay. So let's say one process is trying to wake up, okay, another process, but that process is in sleep state, that is it's not in the active state. So it will try, keep on trying to like that, okay, I am done, you can come, but ultimately that process has not come to that state, or maybe it will not execute. Certain issues have happened that it has gone to the sleep state. So as a result the system will come to a halt and there may be a deadlock as well, okay. So these are the issues that may be there with the semaphore. I think it's only. No, in counting semaphore, the value is not 1. In binary semaphore, the value is 1. Counting semaphore, basically the value of the semaphore will be dependent upon how many number of will be there. Okay. So for example, if we have 4 number of processes, okay. So that time, let's say one of the processes executed. So what happens is, okay. So if suppose, one second, just let me. Example, we have a resource and processes. So here the value of the semaphore will be 4 in counting process. The value of the counting semaphore will be equal to the total number of processes. The working semaphore is a binary semaphore. So whenever process wants that resource, it calls P or wait function, and when it is done, it calls V for signal function. So same way only in the above one also. If suppose one process wants to make use of a available resource or data or whatever it may be, it will first generate a notification P, That means that P will notify to all that you all have to wait. And once it is done, then it will generate another notification V. That means a signal function which will tell that I am done with the critical section. You can come. Now, if the value of S becomes 0, then a process has to wait until S becomes positive. So, if the value of S becomes 0, then a process has to wait until S becomes positive. Okay, let's see. For example, suppose if there are four processes, P1, P2, P3, and P4, and they all okay. This, what is it saying is that suppose if we have four processes, okay, so one has executed. So initial value was 4. Okay, so after one has executed, then there will be a decrement in process P2. It's like they're maintaining a kind of a queue structure. Once P2 has, like they have maintained a kind of an order. P1 has requested first, P2 has requested second, P3 has requested third, and P4 has requested for the fourth. Okay, so P5 has not come only as yet into the system. So that's why the value of semaphore is how much? 4. Now P1, once it has like entered into the critical section, the semaphore value drops. It becomes 3. Okay, so P2, P3, P4 are there. Okay, P5 has entered. Okay, but P2, P3, P4 has already issued the signal. That is which signal? Wait signal. Okay, in order. P1 gave first, then P2, P3, and P4. Now, what will P5 do? Can P5 be given the critical section? No. So till when it will not be able? It will not be able to access the critical section until and unless the semaphore value becomes equal to 0. And when will the semaphore value becomes equal to 0? When each of the processes has executed. Because with first process being executed, from 4 we are having 3. P2, when it will be executed, it will be 1 unit less. P3, 1 unit less. And ultimately with P4, the semaphore value will drop to 0. So once it is dropped to 0, then we can give the allocation for P5. Here the assumption has been taken that they have already given the request for the wait function, the notification, and hence P5 had to let wait. It will not know, right, till when it has to wait. There has to be some signal. So based on that semaphore value, it will get the indication. Because ultimately, once P1 is done, it will generate that signal function that I am done, you all come. But who will come? How will they know? So they will not know, right? So they will be knowing only based on the semaphore value. Okay, similarly, like for P1, P2, P3, P4, it's fine. They know like which one will go accordingly. But for a new process is enter the system altogether, it has to wait until and unless the value of that semaphore becomes equal to 0. I hope that answers. Anyone else? Okay. Did we talk about deadlock before?
No, sir.
Okay. So deadlock is also one of the most important part of operating system and process synchronization. So from the name itself, deadlock, that means certain thing has been locked. It has come to a standstill. Okay, nothing is everything is blocked, you can say. Okay, so deadlock is a kind of a situation, okay, or a problem, you can say, where there are a set of processes which are blocked. They are unable to execute, they cannot go further, they cannot come out of that kind of blockage. Okay, because each process is holding certain resource and waiting also for some other resource acquired by some other process. Okay, so in a deadlock situation, what is happening? A process will have a resource, but it is also at the same time expecting or requesting a resource. That resource again, it is being allocated to some other process. So it becomes a cyclic nature. Okay, it has come to a standstill. So consider an example. Let's say when two trains are coming towards each other on the same track, and there is only one single track, then what will happen? None of the trains will be able to move. Okay, once they are in front each other, can they go back? No. Can they move forward? No, it's not possible. So such a situation is your deadlock in real life situation. So below is a kind of a diagram, if you see. So this is the complete deadlock situation. So here, let's say for example, we have a process one. Process one is having resource one. That means resource one is given to process one, but process one still wants something else. So what he wants resource two. Similarly, process 2, what is it like having resource 2 is being allocated, but process 2 is not happy. He wants resource 1 as well. So despite they are having the resources, they are still looking for some other resource. So ultimately, what has happened? It has come a deadlock, the cycle, a cyclic pattern which is unable to break. So this is waiting, this is assigned, this is waiting, this is assigned. Okay, so they are unable to do the work. Okay, now in which kind of different situations we can have a deadlock. Okay, so these are the various situations. One is mutual exclusion. Deadlock can arise if following four conditions takes place simultaneously. Okay, so if each of the conditions take place at the same period of time, then we say that deadlock is happening. So first is mutual exclusion. One or more than one resource are non-shareable, so only one process can use at a time one or more resource one one or more resource are non-shareable. That means we are unable to share the resource. Like for example, here this resource is given only to here. Okay, it's not shareable, though it's requesting, but it's not shareable, right? If suppose had it been this resource was common to this both the process, then this cyclic pattern we would not have got. Okay, so that is one of the major point here. Mutual exclusion is not with regards to process, here it's with regards to resource. Okay, hold and wait. So this is also same like diagram. A process is holding at least one resource. It is getting one resource, it is being allocated, but still it is waiting for some other resource also. Okay, it's not happy. So it has hold, it is holding one like resource that he has got, but at the same time he's waiting for some other resource also. So that has become like a hold and wait. It is holding the current resource and it is waiting for some other resource which is not available. Then no preemption. That means a resource cannot be taken from a process until the process has itself released the resource. So what has happened? Resource doesn't have the power to come out, okay, from a process. The process has to release. So ultimately what will happen? That resource will remain unavailable until and unless the process doesn't wish to release the resource. So this is also one of the dangerous condition for a deadlock to occur. Then circular weight. So if suppose we have a series of processes which are in circular pattern, so that indicates deadlock. Like for example, here we are having only two processes. So this actually shows you a condition for deadlock. Okay. So these are the four conditions that we have to be very careful that we should not allow it to happen, because any of the conditions, or if all the conditions or any one condition also if takes place, then the chance of having a deadlock, okay, becomes very very strong. Okay, so how are we going to handle the deadlock? So here I think that bankers algorithm comes. So maybe tomorrow I will do that algorithm. I think there was a lot of like request also regarding that algorithm. So maybe tomorrow, hopefully. Uh, so what are the various methods? So there are three ways to handle a deadlock. One is deadlock prevention or avoidance. Okay, so what does it mean? Prevention means what? Means the concept is something that we will not let only that such kind of possibility to arise. Okay, avoidance means we will maintain certain strategy, certain means, or certain algorithm we will design such that we will try to avoid if certain such kind of situation arises. Also, we will try to counter that one. Okay, so one very popular algorithm is the Banker's algorithm. Okay, which is being again uh, designed by Dijkstra, okay, in order to avoid deadlock. So questions may come that write a algorithm designed by Dijkstra for deadlock avoidance. So they may not ask you directly that it is banker's algorithm. So you have to be little bit, you have to understand, okay, the question. Then another one is deadlock detection and recovery. So what has happened here? We are not taking prevention. We are letting it to happen, and but we have certain measures like how we can recover from that situation. So what do we do? There will be certain kind of measures of how we can know that a deadlock has taken place. If the deadlock has taken place, then there will be certain recovery mechanisms. Using those mechanisms, we will be able to come out of the deadlock. Okay, and one is like the most rarest of the rare, generally we don't follow, is that ignore the deadlock, let it happen. Okay, so so what do we do if suppose a deadlock, if the system comes to a standstill, it's not working, we just reboot the system. That basically we do it in Windows and Unix. But for multiprocessing, or sorry, for yes, for multiprocessing, or for, let's say, your systems which are very much critical in your scientific approach, so that time we cannot do, we have to avoid such kind of issues. Okay, so first one, that is the deadlock prevention. So we already know that what are the characteristics for or the characteristics that we can have deadlock. Mutual exclusion. Here mutual exclusion means if suppose the resources are not shareable, then that's this kind of deadlock situation may arise. Hold and wait means what? A resource is being held up by some process, okay, and that process is waiting for some other resource. Okay, so what has happened is it is holding also certain allocated resource that is being given to him. At the same time, it is waiting also for some other process. So as a result, what has happened, it is in a standstill position. No preemption means, let's say for example, a deadlock has taken place but the resource cannot come out on its own. The process has to release the resource from the system. Then only the resource can be free and that resource can be allocated to some other process. But in this kind of situation, resources are, like you can say, dependent upon the release of the process. Until and unless the process doesn't release, the resource cannot come. So this again, it's a no preemption. That means there can be no interrupt in between. Okay, circular wage, that means all of them are waiting in a circular structure, it's a cycle. So once the cycle is there, then we say that deadlock has taken place. Okay, so as we said that there are various mechanisms of how we can handle deadlock. One is the prevention. That means in beforehand only we take certain measures through which we can eliminate deadlock. So one is that eliminate mutual exclusion. So it is not possible to dissatisfy the mutual exclusion because some resources such as tape driver and printer are inherently non-shareable. So it's okay for certain things which are non-shareable. We can make them non-shareable, but for the ones which are shareable, we can definitely for the resources which are shareable, definitely we can share it through a via different processes. Okay, for different. Then another one is eliminate, hold, and wait. So allocate all required processes to the process before its a start of execution. So we are not waiting that beforehand only which process will be given or which process has to wait. What we will do, we will allocate all the required process resources to the or to a process before the process starts its work. Okay, this way hold and wait condition is eliminated. Okay, for example, if a process requires printer at a later time and we have allocated printer before the start of of its execution, printer will remain blocked till it has completed its execution. The process will need to make a new request for resources after releasing the current set of resources. Okay, the solution may, however, lead to starvation. Okay, so what has happened is we will make a situation such that until and unless a process is has not you can say released a resource, he cannot request for any fresh resources. Let's say for example one resource is being allocated to a process. Okay, so that process is holding the resource but it cannot request for a new resource that time. It can request a new resource only when it has released the current holding resource. So ultimately that hold and wait condition is removed. But one thing they have said is that there may be starvation. That means what? The process has released the resource, but there may not be any resources available at that time because all the resources may be allocated to some other processes. So that may be one kind of challenge. Okay. And another thing is that we may, let's say, for example, the process has not started its execution. Okay. Yeah, it has got the allocated it has already been allocated the resource. Okay. But okay, one thing, allocate all required resource to the process before the start of execution. Okay, so we are allocating the resources to the process before the process has started its work. Okay, so this way what will happen, hold and wait condition is eliminated. That means to one process we are giving directly allocating many resources. So ultimately what will happen is that process will basically consume all those resources, and other processes will be we cannot directly request, because here what are we doing in this deadlock prevention. Once the resource is allocated, that resource cannot be requested by any other process. That is one of the most important things. If one of the resources, or if let's say two three resources are allocated for to one process, then those two three processes resources cannot be requested by any other process. So there is no hold and wait. It is given, so once it is given means others cannot shout that give it to me. It will be with that process until and unless he decides to release them. So let's say if that one process has occupied four resources, so all four will be with him, but others they have to keep quiet. They cannot request. So there is no hold and wait. There is no waiting here. So once it starts releasing, then after that others can give a request, and according they will be assigned. Eliminate no preemption. So in the earlier case, we have seen that once the resource is allocated, we cannot break it or interrupt in between only. There is no priority inversion, as we said. That means if a higher priority process comes, then we have the higher priority process also has to wait until and unless the resources released by the process. But in this case, in eliminate no preemption, we can preempt, we can stop in between, release the resource, and give it to the high priority process. So how will the OS know? There will be some priority number, okay, that the OS will be fixing. So accordingly, the operating system will check if, even if suppose one resource has been given to a particular process, but another process comes and that process is holding a higher priority than the current one, then immediately that resource will be truncated and given to the higher priority process. So there is a breakage, okay, according. Then eliminate circular weight. Okay, so each row, oh, here they have said only each row is given a specific numerical number. So accordingly, that process can request the resource in the increasing or decreasing order of those numbering of processes. Okay. Deadlock avoidance, there is an algorithm that will be there. So tomorrow probably I'll do. It's a very big one. We have to, okay, so that I'll check. Yes, I did give assignment, but yesterday I asked the class that should I I mean to say those areas again. I think it was confusing, right? Others they requested, like they asked me that can we do it again, those algorithms and process synchronization. So hence I did. Okay, so another one is the last, like deadlock detection and recovery, the comment sections. Okay, like there's many materials in it, but I'm trying to make it as simple as possible because these things are very technical. If you have seen, also, isn't it? So that's the thing. Like I'm trying to make as more much as simple. There are many numericals also. We will be dealing with algorithms in questions also they ask. So that's why first you have to know the theory, how it works. Okay, what is the main concept behind? So accordingly, you will be able to answer. So let us finish this today and then we can stop. So it's very small only, will be done. So the last one is, that means deadlock detection and recovery. That means a deadlock has occurred, we have to detect it, and then we have to recover from that portion. Okay. So from here, certain question comes like you have to draw a resource allocation graph. That means through that graph, you have to find out whether the deadlock has taken place or not. How to draw the graph? Again, there is an algorithm. So we will be checking in other classes. Okay. So let's say, for example, in this diagram, how do we know that deadlock has taken place or not? So in this case, for deadlock detection, we can run an algorithm to check for cycle in the resource allocation graph. So presence of cycle in the graph is sufficient condition for the deadlock. So do we have a cyclic pattern here? Yes, we do have. If you look here, it's complete cycle. See, it's going on and on. There is no break. Where it will stop, we don't know. Okay, so such kind of condition when it take occurs, we say that deadlock has occurred. So how to draw this graph also I will teach. Okay, so in the above graph, resource one and resource two have single instances. That means resource one is having one instance, process one, and resource two is having another instance, process 2. So once I see here, what is the cycle here? The cycle is R1 is going to P1, P1 to R2, R2 to P2, again to R1. So from where we started, we are coming back again. So here we say that the deadlock is confirmed. Then there may be multiple instances of resources. Okay, so detection of the cycle is necessary but not sufficient condition for deadlock detection. In this case, the system may or may not be in deadlock, varies according to different situations. Okay, so if suppose we are unable to get direct cycle, then also there may be deadlock, but whether it is there or not, that we will not be able to say with certainty. Okay, but if there is a cycle, definitely we can say that a deadlock is detected. Now, if suppose certain situation comes up, then how do we do? Because dealing with deadlock is very much time consuming, even space also, like we have seen. So how do we do? Because deadlock maintain the various information, keeping track of all those information is very much time consuming, even space consuming as well. Okay, so there may be two things. One is killing the process altogether. That means kill all the process, okay, which is involved in the deadlock. That cycle has to be finished. So how will we finish? We have to kill all those processes which are responsible in the deadlock. That means whoever processes have formed the cycle, kill them. Okay, so killing process one by one. After killing each process, check for the deadlock again. Keep repeating the process till the system recovers from the deadlock. So what we need to do is, if suppose the deadlock has happened, we have to check for which program basically this fix. I mean to say, we are unable to do any work. So we have to kill it. We have to keep on killing one by one till the system regains back. That means it can do its work normally. Resource preemption. Okay, so resources are preempted from the processes involved in the deadlock. Preempted resources are allocated. Okay, so here in this case, what do we do is can we have like resource preemption? That means if a process, let's say in this case, this because this resource was requested for P1. So what we can do, sorry, this who? Yeah, sorry. Process one was requesting for resource two. So because of this also it is creating a deadlock. Because of this resource also is creating a deadlock. Resource one. So can we remove this resource two? And whoever wants it, who wants it? Process one wants it. So it's okay. Remove this resource two from process two, and ultimately remove this one. This arc you break it, and ultimately link an arrow from resource 2 to process 1. That means we are giving resource 2 to whom? To process 1. So that way, resource preemption, that means we stop whoever the process getting the resource, we take it off that resource and give it to some other process. So that way that cycle will be broken, and finally we will be able to end this deadlock. So any questions? Hope my classes it is helpful. I don't know, but I'm trying. Okay, thank you so much. I'm really happy. That one, maybe till when it reopens, so maybe the non-verbal communication again.